How are you guys today? Hopefully you're feeling ready to learn some new concentration units. So we're going to be looking at, in second semester general chemistry, some very specific types of concentration units. Again, concentration being how much solute is dissolved in a particular amount of solvent, right on. Whether it's saturated or not, or supersaturated or unsaturated, doesn't matter. We just want to know how much solute there is in a particular amount of solvent or solution total. Now, when we were looking at concentration units in first semester general chemistry, we were always looking at the ratio of the amount of solute, right? How much, whatever species is dissolved, over the amount of solution, which is the solvent plus the solute, solvent usually being water. So pretty much everything we looked at. So if you're a little rusty-dusty in that area, I recommend you go review some of my first semester general chemistry videos on some concentration units, right? Molarity being the big one we focused on. Normality we looked at as well. I don't think you need to review it for this particular series of videos, but if you're curious on normality, you can review that as well. But very much so the percent units, so mass percent, volume percent, weight volume percent, those kinds of things. I recommend before you start these videos, if you don't remember those, go back and watch those real quick. It would be worth the time, trust me. So I wanted to get in a couple very, again, specific units because we're going to need them to look at solution properties later, right? Mole fraction being one of them. Mole percent is just a derivative of mole fraction. So mole fraction we're going to be using when we look at some specific properties of solutions like the vapor pressure, right? We've looked at vapor pressures above pure species, but what about vapor pressures above solutions, which are mixtures? we got a problem here, friends. So mole fraction is a really simple way of looking at it. It's just, again, it's an amount of some specific solute. Let's call that species I. And we use this little kind of a italicized, weird-looking italicized cursive X or something like that. And I've seen people use the capital version versus the small case. Doesn't really matter. So use that to represent the mole fraction, and it's just the amount of that particular solute, right, in moles over the total moles of every species in that mixture. Right? So if you have one solute, you just have two species, the solvent and the solute. But you could have 3 or 4 solutes, right, and the solution, so and the solvent. So it depends what's in there. So a quick little equation here. You don't really need an equation for this. It's more of a definition. So moles of whatever species you're interested in. If there's one solute, that would be the moles of solute over the total, the sum of the moles of all species. So if you had 3 species, you'd have them the mole fraction of species, the moles of species 1, plus moles of species 2, plus moles of species 3. If there's just 2, you'd have the moles of the solvent plus the moles of the solute. Not too bad. That's typically the case. And remember, when you're adding fractions, the sum of them needs to equal 1. Right? All the fractions have to add up to being 1. So if there's 3 species and we know the mole fractions of 2 of them, just subtract those 2 from 1. So 1 minus the mole fraction of species 1 minus the mole fraction of species 2 should be the mole fraction of species 3. Yay! You don't have to solve for all of them. Mole percent, you just take the fraction, multiply it by 100. That's it. Convert that ratio to a percentage. And again, the sum of percents has to be equal to 100%. We did this a lot when we did empirical formulas and things like that. I'd give you the mass percent of, say, 3 out of 4 elements. Well, if you know 3 of them, the 4th one is just 100 minus the other 3. Right? Not too bad. So mole fraction, mole percent. Very logical to do. So some key things to get moles, of course, we probably need the mass, right? If you're given a volume, you'd need the density to get to mass, all those fun little things. Let's do a quick example problem relating mole fraction, which we're going to hit pretty hard when we look at vapor pressures and stuff of solutions. But let's relate it to some of these older units, throw a little bit of review in there for you. All right, get your thinking hats on. Review those before you do this next problem, please. Here's a little, like I said, kind of a problem that connects some review from first semester general chemistry to concentration units of second semester general chemistry. So here's an example. Let's say we've got a 2.55 molar solution of glucose. Okay. Well, let's convert that to mole fraction, right? So what's the mole fraction of a 2.55 molar glucose solution? I will give you the density of that glucose solution, 1.15 grams per milliliter. Didn't specify temperature, so assume room temperature-ish. If you want to be very, very specific, you would state the temperature and find the density for that particular temperature, especially water, right? But this is a solution, and if it's for example, let's say you're given a very, very, very dilute solution, which is mostly water, an aqueous solution, and you're not provided a density or a temperature, you very commonly have to make an assumption about that density, which would probably be pretty close to the density of water, around 1.0 grams per milliliter. So this is obviously, I wouldn't call that a very, very dilute solution in this case. So this would be much more accurate. But we'll see later on we'll be making some assumptions on densities, especially water. All right, here's some steps on how to approach this. This is not a simple one-step dimensional analysis problem, unfortunately, because we're dealing with and this is what we did not do in first semester general chemistry. We always dealt with solute units and solution units. It was nice and simple. But now with these new ones in second semester general chemistry, we're going to be interested in the solvent itself, commonly water. And to extract the information of the solvent, we have to take the fact that the solution is the solvent plus the solute. So we have to do some subtractions and stuff in the process. So here we go. We want the mole fraction, so we need the moles of the solute. In this case, we only have one solute. We need the moles of glucose. That'll be easy. All right, it's right there. This is 2.55 moles per liter. We already know it. Yay! And we need the moles of these, all the components. So we need the moles of the water and the moles of the glucose. So we already know the moles of glucose. Extracting the moles of water out of this is going to be a little more tricky. So here's your process. First, we need to take the moles of glucose, right? C6H12O6, hopefully you knew that, and convert that to grams, right? Let's get the mass of that solute. Then let's use the density of the solution, assuming we've got exactly 1 liter, right? We got 2.55 moles, right? Making this assumption. So 2.55 molar is 2.55 moles of glucose per liter of solution. I don't have room to write glucose there. All right, so we've got 2.55 moles of glucose per exactly 1 liter solution by definition. So we can take that liter of solution and its density and find out the mass of the total solution, right? So now we want to extract the mass of the solvent from that. So just take the mass of the solution minus the mass of the solute, you will get the mass of the solvent, water in this case. If you are not provided the identity of the solvent, you'll have to make the assumption it's water, right? Because they don't even say an aqueous solution here, but that's usually implied. If it's not water, it would be told to you. I mean, it would be stated very clearly it's not water. So we can extract the solvent information from that. So now we got the mass of the solute and the mass of the solvent. Okay. So let's take the mass of the solvent, convert to moles using molar mass. Get your trusty dusty periodic table. We already know the moles of the solute, right? It's 2.55. Then once we have all that, we can do the mole fraction. Take the moles of the glucose over the moles of the glucose plus the moles of the water. That gives you the mole fraction. If you times that by 100, you got mole percent. I want you to attempt this on your own. I'm going to pause it. I'm going to start the problem. There's no way I'm going to get this probably all on one board, but let's start with steps 1, 2, and 3, extracting the information of the solvent out of the solution information. We're going to be doing this several times. You ready? Give it a shot. See what you get. How'd you guys do on the first 3 steps dealing with just the masses right now? You ready? Because we got to convert everything into mass so we can extract, again, the mass of the solvent from the mass of the solution. All right. So let's get the mass of the solute, first glucose. Let's take by definition our 2.55, because it's a 2.55 molar solution. Go to 3 significant figures, so we have 2.55 moles of glucose per 1 liter of solution. Good, that's the starting point. So take the 2.55 moles of glucose, C6H12O6. We need the molar mass of that, so get whatever periodic table. So if you're using a different periodic table, you might get slightly different values. I'm not the kind of professor that likes to truncate or chop off my atomic masses. I don't like doing that. I just like to use the whole thing, and you're limited by the fewest decimal places. So my carbon is 12.011. I've seen 12.0108 before. I should probably convert to that, huh? So that would limit me to 3 decimal places. My hydrogen, 1.00794. So times that by 12, times the carbon by 6, and my oxygen is 15.999994. Times that by 6. Add them all together, limited to 3 decimal places because of the carbon. And so take 2.55 times that molar mass, so you can see the moles cancels out. So we use dimensional analysis in each step, leaving us 459.40 grams of glucose, our solute. Good to 3 significant figures. Not too tough, right? Prep chem stuff. Now, step 2, let's get the mass of the solution using the volume and the density. That's what we use density for, to convert volume to mass or mass to volume. So let's take that 1 liter, by definition, that would be exact, right? We're assuming 1 liter of solution. Convert that to milliliters, 1,000 milliliters per liter. That's exact. And then the provided density of the solution was 1.15 grams of solution per milliliter. So liters cancel, milliliters cancel. You're left with grams of solution. To 3 significant figures, 1,150 grams of solution. There's no non-rounded value, so we don't need that vertical dash line in there. But good to 3 sig figs. Okay. So now, would you agree the mass of the solution is the mass of the solvent plus the mass of the solute, right? So the mass of the solvent would be the mass of the solution minus the mass of the solute, right? So I sort of skipped a step, but mass of solution is mass of solute plus mass of solvent, right? So rearrange it. So we're after the mass of the water. So take the mass of the solution, the 1,150 grams, minus the mass of the solute, the 459.40 grams. Now here we're subtracting, so we're limited by the largest absolute uncertainty. This one is good to the ones place. This one is good to the tens place. So our answer is limited to the tens place. So take 1,150 minus 459.40, limited to the tens place. I get 690.6 grams of water, limited to the tens place. That's when my dashed line is after the 9. All right, so move on to the other steps for me. We can now convert to moles. So we got to figure out, because we want mole fraction, right? Not mass percent, we want mole fraction. Let's convert that grams of water to get moles of water. We already know moles of glucose, and then we can calculate mole fraction. Give it a shot. Not too tough. The concepts here are for, intro chemistry type stuff. It's just putting it all together and thinking about all the component parts that makes it a little tricky. But once you do it a few times, it's not too bad. All right. So we want the moles of water. We already have the moles of glucose, right? We need the moles of every component to get mole fraction. So let's get the moles of the solvent. So we know we got 690.6 grams of water, good to the tens place, which gives us 2 sig figs. Let's divide that by the molar mass of water. So 2 hydrogens, 1.00794 times 2, plus 15.9994. That would limit us to 4 decimal places, so I get 18.015280 grams per mole. Good to 4 decimal places. So we're limited by the 2 sig figs. So when you do that, we can cancel out the grams. Bye-bye. I love canceling out units. Dimensional analysis rocks! We get 38.33 moles of water. There's a lot more solvent than there is solute. That's because it's the solvent, right? So 38.33, good to 2 sig figs. So now we can calculate the mole fraction of species I, which happens to be the only solute we have, glucose. So that'll be the moles of glucose over the moles of the sum of all species, moles of glucose plus moles of water, right? If we had more species, we'd have to deal with that too. That wouldn't be fun. So we know the moles of glucose is 2.55 moles. 2.55 moles plus 38.33 moles in the bottom. We've got an addition and a division. We got to do this in 2 steps. So let's do that addition on the bottom first. Limited, let's see. So our 2.55 moles is good to 2 decimal places, but our 38.33 moles of water is only good to the ones place. Remember, you're limited by the largest absolute uncertainty. So 2.55 plus 38.33 is 40.88 moles of all species total, good to the ones place. So then we can take our 2.55 moles of glucose over 40.88 moles of all species, 3 sig figs on the top, 2 sig figs on the bottom, because we're doing the division, gives us 2 sig figs. I get 0.06237. Good to 2 sig figs. So when we round it, we get 0.062. That would be the mole fraction of a 2.55 molar glucose solution. All right, so you can see it's a little bit of review with a molarity in there, but shows you what mole fraction is. And you'll appreciate mole fraction when we do some properties of solutions later on down the road. If someone had asked you for the mole percent, you just multiply that by 100. So take the mole fraction times 100. So take the non-rounded value times 100. You get 6.237%. Good to 2 sig figs. Rounds to 6.2%. Not too shabby, my friends. Let's look at some more crazy new concentration units.